Today on AI Paper Slop, we are jumping straight into a massive June 2026 release from Nvidia.
Oh, yeah.
It's called Cosmos 3 Omnimodal World Models for Physical AI. And look, if you build physical AI systems, you know the current pipeline is, well, it's basically a Frankenstein monster.
Yeah, totally fragmented.
Right. You stitch together a vision language model for the high-level planning, and then you hand that off to a vision language action model for physical control.
And then you still have to bolt on a separate forward dynamics model just to simulate the future states.
Exactly. But Cosmos 3 just eliminates that entire fragmented pipeline. It is a unified mixture of transformers architecture. It natively processes language, image, video, audio, and crucially, physical action sequences.
All natively.
All natively. Depending on your prompt, it seamlessly acts as a text-to-video generator, a world action model, or, an actual AI robotic policy.
And they just open source the weights today.
Which is huge. It scales from a 4 billion parameter edge model all the way up to a 64 billion parameter supermodel.
It's just a seismic drop for the open source community, honestly.
Truly. So our mission today for the ML engineers and researchers tuning into this deep dive is to unpack exactly how they pulled this off.
Right, without the model just, collapsing under its own compute weight.
Exactly. Okay. We're going to dig into the architecture, the custom attention kernels, and the distributed data infrastructure that allows a single transformer to understand text and robotic kinematics simultaneously.
So to make that unification actually happen, the model first has to translate the physical world into something a transformer can naturally read.
Right.
And that requires elevating action to a first-class modality, like putting it right up there alongside text, video, and audio.
Because, tokenizing text is a solved problem, right? We map words to integers. Tokenizing video means we're just compressing patches of pixels into continuous vectors.
Right.
But tokenizing a physical action gets messy fast. The control space for, say, a self-driving car adjusting a steering wheel is fundamentally different from a dual-arm humanoid robot trying to pick up a coffee cup.
Yeah, and feeding raw, low-level controller data into a general world model just doesn't generalize at all.
Why not?
Well, think about it. A PID value, a proportional integral derivative value, is inextricably tied to the specific gear ratio, the motor weight, and the friction of that exact physical robot.
Oh, right. It's hardware specific.
Exactly. A torque command that gracefully lifts a heavy industrial arm would just violently rip the motors off a lightweight drone.
Ouch.
Yeah, so you immediately hit this massive sim-to-real gap. The researchers sidestepped this entirely by creating a unified action representation.
Okay.
They compress all these diverse physical embodiments into a shared geometric space built on 3 core things.
No.
Ego poses, effector poses, and grasp states.
So they're essentially abstracting away the hardware specifics completely.
Yes.
Instead of calculating absolute motor torques, they use these relative pose pseudo-actions.
Right. They calculate the difference in position and orientation between the current physical state and the previous one. The ego pose tracks the main body or the camera moving through the world, and the effector pose tracks the arms or the limbs.
And they represent both of these continuous movements using a 3D translation vector and a 6D rotation vector, right?
Yeah, exactly.
Let's pause on that 6D rotation vector for a second. Standard robotics usually defaults to Euler angles or, quaternions for representing rotation. So why make the jump to 6D?
It really comes down to how neural networks learn continuous functions.
Okay.
Like Euler angles suffer from gimbal lock, right? Where you lose a degree of freedom when axes align.
Right, which breaks the math.
Exactly. Quaternions avoid gimbal lock, but they have these topological discontinuities.
What does that mean in practice for the model?
Basically, because quaternions map the same physical rotation to 2 different mathematical values, like q and negative q, the neural network struggles to output a smooth learning gradient.
So the math is flipping out under the hood.
Right. If the network is trying to learn a smooth arm sweep, but the underlying quaternion math suddenly flips signs, your gradient just explodes.
Which is bad.
Very bad. So a 6D rotation representation is over-parameterized, meaning it uses 6 numbers to describe a 3D rotation, but it guarantees a continuous, completely smooth mapping space.
So the transformer doesn't get confused by sudden mathematical cliffs.
Exactly. And that makes training across billions of steps significantly more stable.
Makes sense.
Yeah.
And then you have the grasp states, which handle the actual manipulation.
Right.
Rather than tracking relative differences, Those directly encode the current physical state, right?
Yeah, like a 1D value for a simple open or close robotic gripper, or maybe a 15D vector tracking the intricate joint positions of a human hand.
And that brings up the core architectural challenge here. We have this shared geometric concept, but the vector dimensions vary wildly across the different embodiments.
Oh yeah, hugely.
Like a self-driving car only has an ego pose, which gives it a 9-dimensional action vector. But a humanoid robot with arms and hands and a moving body has a 29-dimensional action vector. So if a single transformer backbone is processing a 9D vector for a car in one step, and then a 29D vector for a humanoid in the next step, wouldn't that dimensionality mismatch just totally break the model's internal representations?
You'd think so. But Cosmos 3 resolves it using domain-aware input and output projection layers.
Domain-aware layers.
Yeah. The heavy computational lifting, the actual multi-billion parameter transformer backbone, is completely shared across all the tasks.
Okay.
But at the very edges of the network, they use specialized, learned linear projections for each specific physical domain.
So the car has its own encoder and decoder layer, and the humanoid has a separate one. But they both point to the exact same internal brain.
Exactly. You feed your 9D car vector through the car's specific input projection matrix, and that maps it up into the transformer's high-dimensional latent space.
And the humanoid.
Same thing. You feed the 29D humanoid vector through its projection matrix, and it lands in that exact same shared semantic space.
That's elegant.
Right. The core model reasons over it, predicts the next latent action token, and then a domain-specific output projection layer decodes it back down to the required 9D or 29D physical vector.
And all of these projection parameters are trained jointly from scratch alongside the main backbone.
Yes, all jointly trained.
So because it's all trained jointly, the model essentially builds a universal understanding of physics and geometry in its hidden layers, completely independent of the physical shell it happens to be operating at the time.
Precisely.
But, I mean, merging all these modalities, text, video, audio, and now these tokenized actions, that has to create an absolute nightmare for the attention mechanism.
Oh, it's a massive headache, because understanding a scene and generating a new scene require completely different types of attention.
Right, that's the defining tension of Cosmos 3, isn't it?
Yeah. If the model is processing language or predicting the next physical action, it requires causal attention.
Meaning it can only look backward.
Exactly. It can only look backward at the context. If it peeks ahead, it breaks the autoregressive property. But if it's generating a video frame, it needs bidirectional attention to grasp the full spatial layout of the image.
And in standard causal attention, you create a square matrix of all tokens attending to all tokens. And then you just apply a triangular mask to zero out future tokens.
Right, but your tensor cores are still doing the math on those zeros.
It's just wasted compute.
Exactly. And if you try to throw bidirectional generation tasks into that exact same matrix, the masking logic gets incredibly complex.
So how do they handle it?
Cosmos 3 handles this using a mixture of transformers or MOTI dual tower structure.
A dual tower structure.
Yeah, so there is a reasoner pathway that is restricted to looking backward and a generator pathway looking at the full context.
It's kind of like a 2-lane highway sharing the exact same asphalt.
That's a good way to put it.
Like one lane is driving forward, but the driver is only allowed to look in the rearview mirror that's causal, while the other lane has a 360-degree camera that's bidirectional, and they are processed simultaneously without crashing into each other.
Exactly. To visualize it, imagine a shared digital workspace. One system is frantically writing a chronological log events the reasoner. The other system is painting a detailed canvas based on that log, the generator.
And they share the same memory.
They share the exact same underlying memory resources, reading from the same interwoven data streams simultaneously, but using entirely different rules for what they can see.
But when you use standard operators like flex attention to handle these mixed masks, you usually end up padding the sequences with empty tokens just to make the memory blocks square, right?
Yes, and when you're operating at the absolute limits of your hardware, wasting compute cycles, checking padded data that isn't even relevant just destroys your throughput.
So what did the Nvidia team do?
They recognized that bottleneck and engineered a custom kernel they call two-way flat attention.
Two-way flat attention.
Right. Instead of padding, they flattened and interleaved the reasoner and generator key and value tokens at the individual sample granularity.
So in GPU memory, The sequence is literally zipped together, like reasoner token 0, generator token 0, reasoner token 1, generator token 1.
Exactly. And packing them this way exposes the cross-pathway masking structure directly to a variable length attention kernel.
Well, that's clever.
It is. The reasoner pathway executes a standard causal pass over its designated tokens, and the generator pathway can bidirectionally attend to its own interwoven context block, all without accidentally crossing boundaries into a different sample in the batch.
And the performance gain there has to be substantial.
It is. By eliminating the padding overhead found in fixed-length implementations, this custom kernel yielded a 22% improvement in end-to-end training throughput for the 16 billion parameter nano model.
Wow. A 22% reduction in compute time across a cluster of tens of thousands of GPUs is an astronomical cost saving.
Oh, for sure. Millions of dollars.
But having a highly optimized attention kernel is essential, but feeding it efficiently is a totally different problem.
Completely different.
Training an omnimodal model introduces the logistical headache of heterogeneous datasets. Like, you are combining tiny text captions that are maybe a few dozen tokens with massive, high-resolution video clips that generate tens of thousands of tokens.
And that just shatters traditional distributed training mechanics.
Because the standard approach is to assign an equal number of samples to every GPU in the cluster.
Right. But when token counts vary by over 2 orders of magnitude, a GPU processing 3 massive video files will be grinding away, while GPU processing 50 text captions finishes almost instantly.
And then that fast GPU just sits there idle.
But it's actually worse than just idle time.
How so?
Well, distributed training relies on an operation called all-reduce.
Okay.
At the end of every step, every single GPU in the cluster has to report its gradients at the exact same moment to synchronize the model updates.
Okay.
So if a GPU finishes its text captions in 10 milliseconds, it hits that barrier and waits. Meanwhile, another GPU is grinding on a 4K video for 5 seconds.
And if the step time variance is too high, the NCCL collectives managing that network communication will assume the slow GPU has suffered a hardware failure.
Exactly. The collective times out and your entire multi-million-dollar training run crashes.
Which is a nightmare. To prevent that, I know many pipelines rely on fixed batching, where they just pad the smaller samples with empty tokens to make the batches uniform in size.
Right, but again, that was staggering amounts of memory.
So how does Cosmos 3 solve this?
They solve it at the data loader level with an algorithm called look-ahead packing.
Look-ahead packing. How does that work?
As the data loader builds a batch up to a specific token budget, it evaluates the incoming samples. If the next item in the queue is a huge video file that exceeds the remaining space in that batch, it doesn't just pad the rest of the batch.
Okay, so what does it do?
It diverts the massive video into a temporary look-aside buffer. It then looks ahead in the data stream, grabs smaller samples like text or audio snippets, and crams them into the remaining margins of the batch until it hits the absolute token limit.
Wait, hold on. If the loader is constantly skipping massive video files to prioritize tiny text snippets, aren't you just permanently skewing the training distribution toward text?
You would think so.
Like, wouldn't those massive video files just sit in a backlog forever?
That would totally ruin the model's visual priors, yeah. But they implemented a crucial reset mechanism. At the end of every single iteration, any oversized samples parked in the look-aside buffer are immediately restored to the absolute front of the stream buffer.
Oh, okay.
So they become the very first items packed into the next batch. This preserves the original arrival order of the dataset over the long term, keeping the distribution perfectly balanced.
That's a smart workaround.
Yeah.
And by intelligently packing the margins, they increase the effective sequence length by 8%, recovering all that wasted padding compute.
Exactly.
But keeping the GPUs fed is only part of the memory bottleneck. Once the data is in, we run into the classic long context problem.
Right, the forward pass.
Yeah, during the forward pass of training, you calculate all your intermediate state values, and you have to save those activations in VRAM because the chain rule of calculus requires them to calculate your gradients during the backward pass.
And with omnimodal sequences this long, you will run out of memory almost immediately.
So the standard workaround is activation checkpointing. You discard the intermediate data after the forward pass and just recompute it on the fly during the backward pass.
But the trade-off there is a massive compute penalty, usually adding about 33% more overhead.
Which Cosmos 3 mitigates using selective activation checkpointing, or SAC.
Right. SAC approaches this basically as an economic problem.
It ranks operations based on a flow piece to memory ratio, right? Calculating how much compute time is saved per byte of memory committed.
Exactly. Like in a transformer block, projecting the queries, keys, and values is computationally cheap, but it takes up a massive amount of memory. However, the final attention output is the exact opposite. Computing the attention matrix scales quadratically with sequence length. It takes huge amounts of compute, but the resulting output tensor is relatively small to actually store.
So SAC keeps the attention outputs securely in VRAM to avoid that quadratic recomputation penalty, but it discards and recomputes the cheaper intermediate steps.
Right. It's a surgical optimization that keeps memory usage under the ceiling without destroying the training speed.
Which brings us to the post-training reality. The weights are baked, the model is trained, but serving Cosmos 3 for generation is a completely different architecture than serving a standard LLM.
Entirely different. Generating video or physical action sequences relies on diffusion.
Right.
Which means we have to run this massive transformer forward dozens of times just to generate a single output.
And making that fast enough to function in a real-time robotic control loop is a massive hurdle.
Oh, yeah.
They address this using the VLM Omni backend, specifically relying on a technique called CFG parallel.
Right, classifier-free guidance.
Right. CFG stands for classifier-free guidance. If you are generating an image or video, at every single denoising step, you're actually running the model twice.
Yes.
You run a conditional pass based on the user's text prompt, and an unconditional pass with a blank prompt. The difference between those two predictions is what guides the model toward the actual prompt.
But that means you are doubling your latency for every single step of diffusion.
Right, which is brutal.
So CFG parallel leverages multi-GPU serving by dispatching the conditional forward pass to one GPU and the unconditional forward pass to a completely separate GPU.
Oh, splitting the load.
Exactly. Since those two passes operate independently of each other, they don't need continuous communication.
Right.
They execute simultaneously and only synchronize at the very end of the step to calculate the guided update.
And that concurrent execution nearly halves the latency of the entire diffusion process.
It does.
With the serving optimized, the real question becomes the quality of the generated outputs, which ties directly into the data ablation studies the paper presents on synthetic data generation, or SDG.
This is a huge point. Training data is the ultimate bottleneck for physical AI. The real world just doesn't produce enough clean, annotated robotic data.
So the team augmented the training process with highly curated synthetic data sets built in simulators, synthetic physics interactions, autonomous driving scenarios, and synthetic human data.
And in most ML paradigms, injecting clean synthetic data reliably pushes performance metrics up.
Usually, yeah.
But the ablation study here revealed a profound failure mode tied to the sim-to-real gap.
Yeah, this was fascinating. When they introduced a data set called SDG SynHuman, which is made up of synthetic digital human scenes, it actually degraded the model's performance on real-world human evaluation domains.
It dropped by up to negative 0.69 points.
It is a staggering irony. Our physics simulators are mathematically robust enough to teach a robotic arm how to manipulate gravity, and they can teach an autonomous vehicle to navigate a chaotic intersection.
Right.
But human nuance, the micro expressions, the subtle biomechanics of how a human hand grasps an object, the way weight shifts when we walk, it's all still trapped deep in the uncanny valley.
It really is. The synthetic humans were just slightly off enough that feeding them into the model made it actively worse at predicting real human movement.
It effectively unlearned reality.
Exactly.
But how does that domain interference cross over into completely unrelated tasks? The paper noted that heavily mixing in synthetic robotic manipulation data actually degraded the model's autonomous driving scores.
Right. Well, it comes down to how a unified model builds its internal world representations.
Okay.
If you flood the model with synthetic robotic data, the network starts optimizing its latent space for fine-grained, stationary, close-up manipulation. It alters the model's foundational motion priors. So suddenly, the macro-scale, high-speed, continuous motion predictions required for autonomous driving, they get warped by the physics priors it learned from a robotic arm.
It really highlights that you can't just blindly dump synthetic data into an omnimodal model.
No, the curation has to be incredibly precise. Otherwise, the inherent biases and imperfections of the simulator will overwrite the nuances of the real world.
It operates like a delicate ecosystem. Over-indexing on one synthetic modality introduces a deficit in an entirely orthogonal category.
Exactly.
Well, we've covered the architecture, the custom kernels, and the data balancing act. The real headline here is the accessibility. Cosmos 3 is an unprecedented open-source drop available right now under the OpenMDW 1.1 license.
Yeah, the community now has access to the 16 billion parameter nano model and the 64 billion parameter super model.
Which is amazing.
And crucially, they didn't just drop the base models. They released post-trained variants specifically fine-tuned for text-to-image, image-to-video, and a dedicated robotic policy model, all alongside the Cosmos HETUE evaluation benchmark.
It is an absolute treasure trove for researchers building physical AI. Which leaves us with a final thought to chew on. Throughout this entire breakdown, we've framed Cosmos 3 as a brain engineered to be implanted into physical AI agents, robots and autonomous cars navigating our physical world.
Right.
But look at what it can actually do. It has state-of-the-art capability to generate highly accurate video, audio, and physical dynamics directly from text prompts. Its ultimate utility might not be operating inside the robot at all.
It might serve as the entire simulated universe where the next generation of AI agents is trained.
Exactly. If a unified world model can perfectly simulate the physics, the spatial geometry, and the sensory feedback of a real-world warehouse, you don't need to build a physical warehouse to train a forklift robot anymore.
You just need Cosmos 3.
Right. Can a world model become the very environment it was originally built to navigate? We went from a Frankenstein pipeline of disjointed models to a unified brain. And now that brain might just become the world itself, something to mull over when you pull down those weights.